Hello and welcome to the 18th lesson in the forces topic. In this lesson we're going to be looking at the equation F equals ma, and it includes the required practical, which has two parts, where we investigate the effect of force and mass on the acceleration. For the lesson you're going to need the usual pen, some paper and exercise book to record some notes in, calculator, few calculations using F equals ma, and unless you're needing to watch this video on your mobile phone, turn it off, get it out of the way and avoid any distractions that you can. Into the starter then, I'm going to give you 2 minutes, off you go. One minute left. Units of acceleration then is meters per second squared. So if an object's got an acceleration of 2 meters per second squared, it means that every second its velocity will change by 2 meters per second. Acceleration is a vector, so its direction matters. If you end up with a positive number for acceleration, it means the velocity is increasing. If you end up with a negative number for acceleration, it means that it is negative, it's decelerating. The equation used to calculate acceleration, change in velocity over time taken. So putting some numbers in then for number 4, the car is slowing down from 12 meters per second to 10 meters per second in 1 second. So the change in the velocity is 2. So you end up with 2 divided by 1 second. But because it is slowing down, you do 10, the final speed, minus 12, the start speed. So you get minus 2 divided by 1. So minus 2 meters per second squared. Well done if you got that one right. Outcomes then. The main body of the lesson really is to be able to describe a practical where we analyse force and mass and acceleration. Then once we've got some numbers, and I'll demonstrate the practical for you, we'll have a look at the evidence that we've got and we'll evaluate whether the evidence is enough to show that F equals ma works. Let's check that you're all right with a real life situation calculating acceleration before we move on to the required practical. So we're starting off with an initial velocity of 0. And the cars are speeding up from 0, so they're accelerating. So we can get the final velocity when the white car crosses the line. 67 meters per second, and a final time, a total time to do that.
12:17.
So 12:17. So the acceleration is the change in the velocity divided by the time taken. So 67 minus 0 divided by 12.17 gives you an acceleration of 5.5 meters per second squared. In other words, every second the car is going at a speed that increases by 5.5 meters per second. Let's have a look now at some possible ways that we can measure acceleration in the science lab. There's two main ways that we can set the practical up, but there's various ways that we can measure the acceleration itself. So on this one we've got what's called a dynamics trolley. It's like a little three-wheel trolley, and they're normally made out of wood, but they do have low friction wheels, so they have bearings in the wheels like the wheels of a skateboard wheel that will reduce the amount of friction. So we're trying to reduce the friction there, but we'll still have some friction in that setup. So we can compensate for that amount of friction by giving a slight slope. And the idea is we have enough of a slope that if we just roll a trolley down without any forces on it, it will roll at a steady speed when we give it a bit of a shove. So if we've got it rolling at a steady speed, we know that there's no overall forces on it. So the slight bit of the slope where we've got a bit of gravity is balancing equal and opposite force with the friction from the wheels. So it takes a bit of experiment, and it's never absolutely perfect, particularly if you've got a slight sag in the runway. But it is a nice easy way of compensating for friction, so we can forget about friction in this practical. We then need some sort of force to accelerate it. Now you could use, say, springs for example, or something like that, but that is quite difficult to measure the amount of force. If we hang over some weights on a piece of string, we can calculate that force in newtons by using weight equals mass times gravity. So we can find the number of newtons that gravity is pulling down with, and then we can vary it by adding different numbers of weights on there. If we then put a piece of card that we know the size of it and stick that to the side of the trolley, we can put light gates in and use the light gates to measure the acceleration. So what would happen is that the first light gate that the blue card goes through will cut the light off. The computer will then calculate the amount of time that it's taken, and then you input in the size of your card, so you've got distance divided by time, so you can get a velocity at the first light gate. Then the same thing happens at the second light gate. The computer can measure the amount of time between the two light gates, and it can do change in velocity over time taken. Now what that means is that the computer will give you the acceleration, so we don't have to worry about the actual calculation of acceleration here. We can let the computer do the work. Newton's second law then. Acceleration of an object is directly proportional to the resultant force exerted on it and inversely proportional to its mass. Sounds complicated, but all that means is the harder you push something, the faster it'll speed up. So if you double the force on something, you will double the acceleration. The greater the mass of an object, the more force that's required to accelerate it. So if you've got a more massive object, like a car that's full of passengers instead of being empty, the same force will not give it as much of an acceleration. So we'd say that the acceleration is inversely proportional to mass. If you doubled the mass, then the acceleration would halve if you've kept the force the same. Writing that as an equation for Newton's second law. So if a question says to you in the exam, what's Newton's second law? It's absolutely fine to put force equals mass times acceleration. We measure the force in newtons, the mass in kilograms, and the acceleration in meters per second squared. And we can write that as F equals ma. That's Newton's second law. The required practical activity then, there's two parts to it. So investigating the effect of varying the force on the acceleration and the effect of varying the mass. So I'm going to do this as two separate practicals, and I am going to show you a couple of different ways that we can do it. Part one is going to be varying the force and measuring the acceleration. So in part one I'm going to keep the mass constant, and then part two I'm going to change the mass and measure the acceleration, this time keep the force constant. So we'll get two separate practicals that we can do two separate graphs, and then we can look at the relationship between them. Before I start with the main part of the practical, I'd just like to talk you through the air track and the way that the air track works. So we've got an air track, there's a blower down at that end, and here along the track there's little holes so that you get a cushion of air. So if I switch on the blower, and I'll just use one here so you can see, because of the cushion of air that we've got, it pretty much eliminates friction, so that should be moving at a steady speed there. So we don't need to put this on the slope. We've got rid of friction or reduced friction by a lot just using that cushion of air. So that's how the air track works. Switch that off. So if I just pick up my phone and just show you a close-up of the equipment I'm going to use to measure the acceleration. Though this equipment, this data logger here, will measure the acceleration for us. So when we write this experiment up, we're just going to say we use a light gate connected to a data logger or computer, and that will tell you the acceleration directly, so we don't need to go into the detail of measuring the acceleration. So there's the light gate. When something passes between the light and the sensor, it knows it's there and it times how long it's there. So on the glider, there's the glider sitting on the cushion of air, piece of cardboard on it. That piece of cardboard there is 2 centimeters wide, and so is that piece of cardboard there. So as it goes through the light gate will do distance divided by time for that bit, so it can work out the velocity at the start. Distance divided by time for that bit, work out the velocity at the end, and it will also time the gap between them. So then it can do change in velocity divided by the time taken, and that'll just show up as an acceleration with the units on there. So that's that bit. That's how the data logger and the light gate works, and that's how the air track works. I'm going to talk you through this setup, which you also might see. If your school has got an air track, it is probably the best way of doing it. So I will show you an air track as well as a trolley on a friction compensated slope. I'm going to talk you through the purpose of each one, and then at the end I'm going to give you 2 minutes to make a note on the purpose of each bit of equipment. The air track then, the air track and the blower, the blower, there's a vacuum cleaner in reverse, forces air into the air track, and the air track is like air hockey table. It's got holes in it. So the air blows out of the holes, which gives a cushion of air. So the whole purpose of the air track and the blower is to eliminate almost friction. You will get a tiny bit of air resistance, but very few frictional forces on there. We've got the glider, which is the thing that's sitting on top of the air track, and a piece of card. The card is there, it's a set distance. The piece of card I'm going to use is going to be 2 centimeters, but I'll talk you through that in the video. The piece of card will go to the light gates, so that will enable the light gates to calculate two velocities and find an acceleration. So the light gates are there to help you find the acceleration. The string then connects the glider to the weights, so the weights give you the force, that's your force N. And the bench pulley, if we didn't have a pulley there, we'd have friction as the string rubbed over the end of the bench. So the bench pulley there is just to reduce the friction on the string as the force is pulling it down. 2 minutes then, make a record of that, explain what the purpose of each one is. If you get stuck, you might have to rewind the video. There's 10 seconds left. I'll just give you a quick check then. So the blower, the air track and the bench pulley have all got the same purpose, that to reduce friction. The card and the light gates will enable a computer to measure the acceleration, and the weight stack provides the force. Let's first look at the method of investigating F equals ma just using a ramp and a trolley as opposed to the air track. So if we look at this trolley now, I'll give it a shove. What should happen is when I let go, it should fall. So it should carry on going at a steady speed, but obviously it doesn't because there's friction in the wheels, and you can hear the friction in the wheels converting that kinetic energy to sound and heat energy, so we know there's some energy loss. So what we need to do is we need to compensate. And the way that you can compensate is to put some sort of slope on. There's no exact science to this, I'm going to do it by trial and error. So I'm going to prop that up. And what I'm looking for, if I've compensated for friction properly, it should roll down that slope at about steady speed. Well, I think that's pretty good, to be honest. It never worked first time. Let's give it a go. That's not bad. I think it might be slowing down slightly. I can use the light gate and the data logger to test that. If I get it measuring acceleration, and these are 2 centimetres that I'm using here, these bits of card that are sticking up. Go when ready. I can give it a shot. I should get an acceleration of 0 if I've got it right, or at least pretty close to 0. Oh, I did get through. Let's just see what we've got. 0.04. That's pretty good. What I'll try is, I need a little bit less. And the problem I've got is it's slightly bowed. If I just move my light gate and I look at this area, because it's slightly bowed, I'm just going to try it there and just see if the acceleration is a tiny bit smaller. So let's give it another go. I'm looking for getting it as close to 0 as possible. Now I got minus 0.06, so it's slowed down. Just going to come back a bit. Just see if I can get a sweet spot. Give it another go. Oh, well, I'm going to have to show you that because I don't actually believe that myself. So 0.00, so I've got no acceleration. So what I've got now is I've got a slope that's compensated for friction. So we've put a bit of a slope on it. The amount of gravity that we're using from that slope is going to be equal and opposite to the friction from there. So now what I can carry on doing is carry on doing the F equals ma practical. So the first practical that I do, I keep the mass constant and I put some weights to give us an accelerating force. I tie that on there, weights over the end, weights would fall and it would accelerate, and I'd just change the force and measure the acceleration. And then for part 2, I keep the force the same, but I'd apply more mass on here. So I'd increase the mass and see how the mass affects the acceleration. This simplified apparatus there is the main way that I'm going to do the practical for you when I demonstrate it, just because it's the simplest to understand and it's the most likely version to be on the exam. So as a quick progress check then, looking at that there, will you tell me why the air track was horizontal? It was flat, but the wooden board needs to be on a slight slope. before we have a look at the answer to this then, there is a disadvantage with using this apparatus. Because the two pieces of the two sticky up bits of card are quite close together, it can be slightly more inaccurate than using two light gates where you can have them further away. But there's a big advantage in that it's quite simple. So the air track's horizontal because it's using a cushion of air to get rid of friction. Here we need in a slight slope to provide some part of gravity to cancel out the friction in the wheels. Part 1, we're going to look at varying the force on the glider or on the trolley and see how that affects the acceleration. So I want you to think then, if they have been mentioned already, what's the independent variable, the dependent variable, and some control variables, if you could list them. Independent variable, that's the force. So we're going to change the force, so we're going to put different weights on the end of the string so that we've got different forces accelerating the glider or the trolley. Dependent variable, so that's going to be the variable that you measure. We're going to measure the acceleration. And control variables, going to keep the mass the same, light gate positions. If you're thinking about the version of the practical where you're using a slope, a friction compensating slope, then that slope needs to be kept the same during the practical as well. Let's look then now at the first part of the F equals MA practical. In this practical, we're going to keep the mass of the glider constant and we're going to use a force to accelerate it. So we're going to measure F and we're going to measure A, and then we can plot a graph of those and we can see the relationship between the force and the acceleration, which means we need to keep the mass constant. So I'm going to measure the mass of the whole lot. That comes to 380, but I'm going to use a falling weight to accelerate it. That's going to give me the force. I'll show you it going over the pulley at the end in a second. But the whole lot is going to be accelerated by gravity. So I want to measure the whole lot. And I'm going to go, might end up going pretty quick at the end. So the greatest weight that I use is that. So that I've got there is going to be the constant mass all the way through. And that's 480 grams. I'll convert that into kilograms straight away. So 0.48. You don't need to make a note of that. I'll make a note of it for you. 0.48 kilograms is the constant mass. So that's going to sit on the air track. Cotton goes down here. I'll show you a close up in a second. And then we've got the falling mass there. So here, got a bench pulley. Again, that's to reduce friction. And then hanging over there, we've got our force. Our falling masses are going to give us the force. Weight equals mass times gravity. So we'll have a force there and I can vary it. And then that force is going to accelerate that mass, and the data logger is going to give us the acceleration. So I might do repeat readings, I might not. We'll just see how smoothly it goes. If it goes nice and smoothly, we'll have time. If not, I might not. Again, if you want to record the forces and the masses, you can, but it will be on on a slide after the video. So what we've got there is, right, we've got 100 grams falling mass. 100 grams is 0.1 of a kilogram multiplied by gravity. We're going to call it 1 Newton. So we're going to start off with 1 Newton. 1 Newton force will measure the acceleration. Something you've got to be careful of is where we're putting the light gate, because what I don't want the masses to hit the ground before it's reached the light gate, because then it won't be accelerating, it'll be going at a steady speed. So I'm only going to have to go that distance, which is bigger than the meter that we've got for the drop. So let's see if it goes smoothly. It'll get noisy and that'll release. See if we get a value. So this is a force of 1 Newton. Pretty quick. Right, didn't get a register. Send it back. Apart from that, it worked fine. Apart from we've got no numbers, all good. Totally my fault. I didn't press go for ready. So there we go, we're all ready. 1 Newton. See what we got? 2.29 meters per second squared. I'll write that down, 2.29 meters per second squared. That was quite a large force, but that's my greatest force, so all the others are going to be smaller. So what I need to do now is, right down there, I need to reduce my force. So it was 0.1 newtons, now it's going to be 0.08 newtons. Sorry, 0.8 newtons. 1 newtons before, 0.8 newtons now. And I've got to remember, because I've got to keep the mass that's been accelerated the same. I'll try and use a small piece of blue tack because I didn't weigh it. I just need to add that onto there so that the amount of mass that's been accelerated by gravity is still the same. Hopefully that doesn't fall off. Should be okay. We'll get ready for the next one. And it's waiting. Air track on. There we go. See what we got? 1.57, it's less, thank goodness for that. So 1.57 meters per second squared. Reduce the force to 0.6. Remember to keep your mass that's been accelerated the same. I'm just going to stick that one on the other side this time, try and keep it balanced. Now we've got 0.6 newtons, and I'm after decreasing again. We've got a smaller force, we'd expect a smaller acceleration. What we got? 1.23. Going too well. Almost going too well. Something's going to go wrong. Reduce my force to 0.4 newtons. Make sure that I keep the mass that's been accelerated the same overall. Go. Right.
0.77. Pleased with this so far. And one last one. This will be 0.2 newtons. Keep the mass, I know I'm getting boring. Keep the mass that's been accelerated the same. I'm just going to double check that that's 0.2 and not 0.1. The mass hanger might only be 0.1, so I'll double check and make sure that I've got it right on the results table. Or 0.37. Check this one. Yeah, 29. So looking at that data, 1 Newton 2.29, 0.8 1.57, 0.6 1.23, 0.4 0.77, and 0.2 newtons is 0.37. So I'm getting a pattern that's falling all the way down. Looks good. What I'm going to do is I'll do some repeat readings, but I won't film them because it'll take too long. I'll just put them on the results table so we can look at them later. So that's the first part of the practical.
Here's the results table for part 1. We've got the force on the left, so we've gone from 0 newtons up to 1 newton, so that's a range of 1 newton. I've added 2 extra columns where I've done repeat readings for you, and then at the end we've got a mean acceleration, which goes from 0, so when we've got 0 force we've got 0 acceleration, up to 2.3 meters per second squared. So to find the mean, I've added up the 3 values and divided by 3. Apart from where I've got an anomalous result, so that 1.44 is considerably lower than the reading I've got that I took first and third. So I've not included it at all in the average. I've got rid of it. So remember, doing repeat readings reduces random errors because you can get rid of them when you find the mean. So that gives me a mean of 1.56. If I'd have included the 1.44, it would have brought the mean down. It probably would have given me an anomalous point on the graph. Plotted then for you. If you get time, you can plot your own. Force along the bottom. So the force in newtons there is the independent variable. It's the thing that we changed. Then on the y-axis, we've got the acceleration, so that's the dependent variable. Remember in this experiment that the mass is kept constant, the mass is a control variable. We see we've got a nice straight line there. So if we add a best fit, there it is. I've tried to go sort of through the middle of the points with a straight line. I've made sure that I've used the point in the origin, the 0 force, 0 acceleration point, because I know that is absolutely spot on, because no force gives you no acceleration. So I've used that point. I've made sure I've gone straight through the middle of that point, and then I've tried to go through the middle of the others. So you can see there that increasing the force increases the acceleration. In fact, in maths you'd say it's a positive correlation, but we know more than that. It's directly proportional. Directly proportional is a straight line that goes through the origin. It goes through 0, 0. So doubling the force doubles the acceleration. What I want you to do now, I'm just going to give you 1 minute, is to state the independent, dependent, and at least 2 control variables. Okay, just 20 seconds left. let's see what you got then. So the independent variable, the thing that we decided to change, is the mass for part 2, and for the dependent variable, it's the acceleration. You can see from the way that the question is worded, it does help you out. The dependent variable, the thing that we're going to measure, is the acceleration. And 2 control variables, well, you could have the force this time, position of the light gates. If you're using a friction compensated slope, it's the gradient of that slope.
Part 2 of the F equals MA required practical. This time we're going to keep the force that we're using to accelerate the glider constant. That's 20 grams on there at the moment, so that's 0.02 kilograms, so 0.2 newtons. So the force I'm going to use is going to be 0.2, and that's going to be the same all the time. So that's going over the pulley to reduce friction. We've also got the air track reducing friction. And this time we're going to increase the mass. So the mass as it stands at the moment is 0.38 kilograms. And then after each one, I'm going to increase it by 40 grams so that I've got 5 readings. And I'll do some repeat readings, but I'll probably just add them onto a results table at the end to save you having to spend too long watching this. So let's go. Air track on, reduce the friction. Data logger is going to record the acceleration direct for me. So this one, first one off we go. So what we've got, 0.45 meters per second squared. And then do it again. This time we're going to increase the mass. Put a rubber band on there just to make it a little bit easier for me to put those on there. Try and keep it fairly equally balanced. So the mass now is going to be 0.42. So we've increased the mass. We've got more mass that needs accelerating by the same force. We should end up with a smaller acceleration. Fingers crossed. And there we go. No. 0.41 decrease, that's a good sign. 0.41 meters per second squared. To increase the mass now, it's been accelerated. Put another 20 grams on and another 20 grams on, which gives us a total mass of 0.46 kilograms. Definitely appears to be accelerating at a slower rate now. 0.39, so now 0.39. Another 40 grams on. Should really start to be noticing the difference in the acceleration now. Not 0.37. And the last one, before I do some repeat readings. swing in. My fault. If it went perfectly, it wouldn't be the same. I didn't forget to press the go button. You'd be thinking I'd edited the video if it went too smoothly. That's it, part 2. How does the acceleration depend on the mass that's been accelerated with a constant force? You'll get the results table in a minute. I will have put some of the repeat readings in when I've done them, and then we can have a look at the data and have a look what the graph looks like. Here's the results then for part 2. We've got the mass varying from 0.38 to 0.54 kilograms. Again, I've done a couple of sets of repeat readings for you and then found the mean at the end. Just have a look at those numbers, see if you can spot any potential anomalous results there. So we got that one where the 0.25 there's too low, so it's not been included in the mean. We've just done the average of 0.33 and 0.35. And then that 0.45 there, the 2 repeat readings that I did were higher, so I just used those and got rid of the 0.45. We can then see this as a graph. So there you go. Mass this time along the x-axis, so that's the independent variable. We changed the mass, and then we measured the acceleration, so that's the dependent variable. And you can see this time, as the mass increases, the acceleration decreases. It's more difficult to accelerate a bigger mass. If you look at that then, you might be tempted to do a best fit straight line with your ruler there. But if you look carefully, there's a curve. Sometimes it helps if you put your face on your paper, or in this case, the face on the screen, and look along the line of the points, and you'll see that there's a gentle curve. So freehand, best fit curve should end up looking something like that. So as we increase the mass, the acceleration decreases. It's a negative correlation. So we've got 2 hypotheses then that come from the start of this practical. So a hypothesis, scientific question that you can then go on and get some data to work out whether it's true or not. So the first one is the acceleration is directly proportional to the applied force when the mass is constant. And the second one is the acceleration is inversely proportional to the mass of an object when the force is constant. So first question for you, does the data support these 2 hypotheses? I'm going to help you answer that question at the end actually, because we need to look at the graphs again. Was there any anomalous data, and how could you improve the reliability of the data? Now we saw there was anomalous data, and the anomalous data stood out on the best fit on the repeat readings. So often you do repeat readings, you can spot random errors, and that's your anomalous data, and then we don't include those in the mean. So yes, we did get those. We got 3 of those in total. Improving the reliability. So what that means is, what else could you do? What could you do differently? What extra things could you do to make the numbers, the data that you've collected, tell you a better story, be more reliable, something you could depend on a little bit more? Often, one way that you can improve the reliability, and this is particularly true for the experiment where we varied the mass, if we'd done a bigger range of mass, it would have helped us to draw that best fit curve. So we could have done a bigger range. We didn't manage to get a mass doubling. It's quite difficult on the air track to put enough mass on without you losing your cushion of air. But if we'd have done it with the friction compensated slope, even though it's not as precise, the measurements there, we could have had a bigger range of data. And again, doing repeat readings, doing more repeat readings helps you get rid of those random errors. Let's go back to the first question then. Does the data support these 2 hypotheses? So there's part one. From that we can see how the force affects the acceleration. So we know that that was a best fit straight line. So we put a straight line through it. Now, because that's a straight line that goes through the origin, it is directly proportional. So that does support the hypothesis. You can do further work on there. You can actually look at the numbers using the graph. Usually this is a higher question, but there's no reason why I can't talk you through it now. I'm just going to look at where the graph is for 1 Newton. So I've just done a purple arrow there, and I've done it up from 1 Newton. And then so I can get a nice comparison, I've just picked half of 1 Newton. So I can compare 1 Newton to half a Newton. So at half a Newton, I've got an acceleration of 1 meters per second squared. And at 1 Newton, I've got an acceleration of 2 meters per second squared. So if I double the force from 0.5 to 1, I've doubled the acceleration from 1 to 2. So that's nice and reliable. It's good. It works spot on. So doubling the force doubles the acceleration. So we'd say that the acceleration is directly proportional to the force. That's the easier of the two. So let's look at the next one now. We've got its curve, got its mass on the bottom, acceleration up the side, and we've got a curve. So as the mass goes up, the acceleration goes down. Let's try and do this with numbers then in the similar way that we did before. If I put an arrow on there, I'm just going to pick 0.43 kilograms. I've picked that number just because it falls nicely on the line there at 0.42 meters per second squared. And then I've picked 0.54 again just because it falls nicely. Then I'm going across, then I'm going across. So at 0.54 kilograms, I've got 0.34 meters per second squared, and at 0.43 kilograms, I've got that. So when I've gone from 0.43 to 0.54, it's gone up by a factor of 1.6. Inversely proportional should mean then that the acceleration has fallen by a factor of 1.6. So let's have a look. It's fallen, the acceleration has decreased by a factor of 0.42 divided by 0.34. That's 1.2. So it's close, but it's not spot on. So I would say that it supports it, but you really need more evidence for it to be reliable. A greater range, a greater change there of the mass. If we could at least get to a state where we've got a doubling of mass that we could see on the bottom, that would make it a bit more reliable. It does support it, but it's not completely convincing.
2 minutes then to do this 4-mark part of an exam question. It's not about the physics, this question, it's about how science works. It's about the results and the data and the way that the practical was carried out. One minute left. Okay then. So what you've got to do first is to identify two mistakes. And the first thing I do if I was doing this on the exam paper is put a ring around where I think there's something that's a mistake. So I'll put you the mark scheme there. The first thing you need to highlight is that 1.26667. The student has put too many significant figures down. The number of significant figures that you put in a reading should reflect the precision in which you've taken it or the resolution of the instrument that you've used. So it should be the same all the way down. It's a calculated value, and when we measured the acceleration in test 1, test 2, test 3, we just did it to two significant figures, one decimal place. So it should be to the same number, and the number that it should be to is 1.3. So saying which one it was and saying that it should be 1.3 will get you 2 marks. The next thing to notice there is we've ended up with an incorrect mean on the last resultant force, the 0.98 newtons one. Because there's quite an obvious anomalous result of 7.2 on test 2, you shouldn't have used that. You should have just not used it and then averaged the other two, which would have given you a recalculated mean of 6.4. So 1 mark for highlighting that 7.2 and saying it shouldn't be used, and the correction is to just do the mean without it, so you get 6.4. Just going to leave you with the summary then. We've got the equation F equals ma, that's the equation that represents Newton's second law. We've got the first graph to show that the acceleration is directly proportional to the force, and the second graph that shows the acceleration is inversely proportional to mass. We've got the setup of the practical using the air track, and just a reminder at the bottom there of what part 1 and part 2 of the practical was. Well done. I'll see you next time for the next lesson on forces.